rendered world. In the world of computer science, there is a concept known as frustum culling. It is a technique used in video game design to save processing power. The logic is simple. If the player isn't looking at it, don't draw it. When you play a game like Grand Theft Auto or Cyberpunk, the city behind your character's back doesn't actually exist. It is just code. It is a void of potential data waiting to be executed. Only when you turn the camera, when you make an observation, does the engine quickly render the buildings, the cars, and the people. It creates reality just in time for you to see it. We accept this in computers because we know they have limits. They have a finite amount of RAM and processing speed. They cannot simulate an entire universe down to the atom all at once. So, they cheat. They optimize. But what about our universe? What about the chair you are sitting on? The wall behind you? The stars in the night sky? For centuries, we believed the physical world was solid. We believed that if every human, every animal, and every camera disappeared tomorrow, the universe would keep ticking along exactly the same way. A rock is a rock, whether you look at it or not. That is the comforting assumption of classical physics. It is the bedrock of what we call realism. But what if I told you that assumption is wrong? What if I told you that physicists found a glitch, a crack in the code of reality that suggests our universe operates exactly like a video game engine? It sounds like conspiracy theory nonsense. It sounds like the plot of a sci-fi movie. But this isn't fiction. This is quantum mechanics. And the proof lies in a single, deceptively simple experiment that has haunted scientists for over 200 years. It is an experiment that defies logic, violates the laws of time, and forces us to ask a terrifying question: is reality real? Or is it only real when we are watching? This is the story of the Double Slit Experiment. And be warned, once you understand it, you can never unsee it. Chapter 1. The War of Light 1704-1801. To understand the glitch, we first have to understand the system. And the most fundamental part of that system is light. Light is everything. It is how we perceive the universe. It is the carrier of information. But for most of human history, we didn't know what it was. In 1704, the giant of science, Sir Isaac Newton, published a book called Optics. In it, he declared with absolute confidence that light was made of particles. He called them corpuscles. Little bullets of energy shooting through space in straight lines. It made perfect sense. If you shine a flashlight at a wall and put your hand in front of it, you get a sharp shadow. The light particles hit your hand and stop. The ones that miss your hand keep going and hit the wall. It's ballistic. It's mechanical. It's intuitive. Because Newton was the smartest man who ever lived, the scientific community bowed their heads and agreed. Light is a particle. Case closed. But nature doesn't care about reputation. While Newton was basking in his glory, a Dutch physicist named Christian Huygens was whispering a different theory. He looked at water. He looked at sound. He saw that energy traveled in waves. Ripples in a pond don't move in straight lines like bullets. They spread out. They bend around corners. He suggested that light was a wave, vibrating through an invisible medium. But Huygens couldn't prove it. And you don't go against Isaac Newton without proof. So, the wave theory died. For 100 years, light was a particle. Until 1801. Enter Thomas Young. Young was a polymath, a man who could read hieroglyphs and dissect eyes, but his greatest contribution to history was a simple setup in a dark room. He wanted to settle the debate once and for all. His experiment was elegant in its simplicity. He took a light source, sunlight, coming through a tiny hole in a window blind, and he placed a card in front of it. In that card, he cut two incredibly thin, parallel slits. Behind the card, he placed a screen to catch the light. Here is the logic. If Newton is right and light is made of particles like little tennis balls, then the light should pass through the two slits and hit the back screen in two distinct strips. You fire balls through two holes, you get two piles of balls. It's common sense. But if Huygens is right and light a wave like water, something else should happen. Imagine a wave of water hitting a barrier with two holes. The wave forces its way through both holes. On the other side, two new waves emerge, spreading out in semicircles. These two waves will then crash into each other. This is where the magic happens. It's called interference. When the crest, the top of one wave, meets the crest of another wave, they combine to make a bigger wave. This is constructive interference. But when the crest of one wave meets the trough, the bottom of another wave, they cancel each other out. They destroy each other. The water goes flat. This is destructive interference. If light is a wave, Thomas Young shouldn't see two strips of light. He should see a pattern of many stripes, bright bands where the light waves amplify each other, and dark bands where they cancel each other out. This is known as an interference pattern. So, Young opened the blinds. He let the light hit the slits. He looked at the back screen, and there it was. Not two lines, but a series of bright and dark bands stretching across the screen. A barcode of light. Young had done the impossible. He had proven Newton wrong. Light was not a bullet, it was a ripple. The universe was analog, fluid, and wave-like. The scientific community had to rewrite the textbooks. The war was over. The wave theory had won. Or so they thought. Chapter 2. The Quantum Revolution, 1905-1927. Fast forward to the early 20th century. The Industrial Revolution has built machines of steel and steam. We thought we had physics figured out. But then, a patent clerk in Switzerland named Albert Einstein decided to break everything again. In 1905, Einstein was studying something called the photoelectric effect. This is the phenomenon where shining light on a metal surface pushes electrons off the metal. It's the technology behind modern solar panels. But there was a problem. If light was purely a wave, then a dim light shone for a long time should eventually build up enough energy to knock an electron loose. Like small waves slowly eroding a cliff, but experiments showed that didn't happen. Only light of a specific frequency color could knock the electrons off, regardless of how bright or dim it was. Einstein realized that the wave theory, the one Thomas Young proved, couldn't explain this. The only explanation was that light hit the metal like a punch, like a rock, like a particle. Einstein called these packets of light quanta, later named photons. He proved mathematically that light travels in discrete, chunky packets of energy. So now, physics was in a crisis. A deep existential crisis. Thomas Young proved light is a wave. Albert Einstein proved light is a particle. They were both right, and they were both wrong. How can something be a continuous ripple and a solid bullet at the same time? It's like saying a cylinder is both a circle and a square depending on how you look at it. It violates the law of non-contradiction. This confusion birthed a new field of science, quantum mechanics. the study of the very small, where the rules of the big world stop working. The founders of this new science, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, decided to investigate further. They thought, okay, light is tricky. It's energy. Maybe energy is weird. Let's try the experiment again, but this time, let's use matter. Solid stuff. Stuff that has mass. They chose electrons. Electrons are the building blocks of reality. They are the tiny planets orbiting the nucleus of an atom. They have weight. You can count them. They are definitely, absolutely particles. If you throw a stone, it's a stone. If you throw an electron, it's a tiny stone. So they set up the double slit experiment again. But instead of sunlight, they used an electron gun, a device that shoots a stream of electrons like a microscopic machine gun. They placed the barrier with 2 slits. They placed a detector screen at the back that lights up whenever an electron hits it, like a pixel on a TV. They expected the result to be boring. They expected to see 2 bands of electrons on the back screen, because particles travel in straight lines. They fired the gun. Rat-a-tat-tat. The electrons poured through the slits. But when they looked at the screen, the blood drained from their faces. There, on the phosphorescent screen, was not 2 bands. It was the interference pattern. Bright, dark, bright. The electrons, these solid chunks of matter, were behaving like water. They were rippling. They were interfering with each other. How is this possible? Imagine firing tennis balls at a wall with 2 holes. You expect 2 piles of tennis balls. But instead, you find tennis balls scattered all over the back wall in a complex geometric wave pattern. It implies that the tennis balls somehow turned into liquid, flowed through the holes, crashed into each other, and then turned back into solid balls when they hit the wall. The scientists were baffled. They thought, maybe the electrons are bumping into each other in the air. Maybe the stream is too thick, like a crowd of people pushing through a doorway. So they decided to do the ultimate test. They would slow things down. They would fire the electrons one by one. Click, an electron is fired. It hits the screen. 1 dot. Click, another electron, another dot. Click, click. They let this run for hours, maybe even days. Each electron is alone in the universe as it travels from the gun to the screen. There is no other electron to bump into. There is no water to create a wave. It is a solitary traveler. Logic dictates that since they are alone, they must travel in a straight line. Over time, 2 piles should form. But when the scientists developed the final image, the impossible stared back at them. Even when fired one by one, the interference pattern appeared. This result is so profound that it defies human intuition. It means that a single electron leaves the gun as a particle and then dissolves. It becomes a wave of potential. This probability wave travels through space. It goes through the left slit. It goes through the right slit. It goes through both slits simultaneously. And it goes through neither. The single electron interferes with itself. The ghost of the electron going through the left slit crashes into the ghost of the electron going through the right slit. And then, only when it hits the back screen, does it decide where to land. It collapses back into a single point of matter. This was the birth of superposition, the idea that a particle can be in multiple states and multiple locations at once. But the human mind hates mystery. We want to know how. Which slit did it really go through? The math says both. But our brains say that's impossible. So, the scientists decided to get sneaky. They said, we are not going to guess. We are going to look. They set up a measuring device, a sensor, a camera, a detector right next to the slits. They wanted to catch the electron in the act. They wanted to see with their own eyes, which hole the particle chose. They turned on the machine, they turned on the detector, they pressed the button, and the universe reacted. Chapter 3. The Collapse, the Observer Effect. The setup was perfect. The electron gun was primed. The slit barrier was ready. But this time there was a difference. A spy had been installed. The scientists placed a detector right next to the slits. Its job was simple. Just look. Tell us which path the electron takes. Does it go left? Or does it go right? If the electron is a wave, the detector should see a ghostly smear of energy passing through both slits at once. If it's a particle, the detector should see a single dot passing through one specific hole. They turned on the beam. Click, click, click. The detector beeped. It saw an electron go through the left slit. Then it beeped again. It saw an electron go through the right slit. Left, right, left, right. The scientists cheered. Aha! It's a particle! It's not a wave! It chooses a path! The mystery was solved. The electron was just a tiny ball of matter all along. The wave theory was a mistake. But then they looked at the back screen. Remember, when no one was watching, the screen showed the beautiful, complex interference pattern, the signature of a wave. But now, with the detector turned on, the interference pattern was gone, vanished, deleted. In its place were two simple, boring bands of electrons. Two piles. The particle pattern. The room went silent. The implications were horrifying. Think about what this means. When the scientists weren't looking, the electron acted like a wave. It explored all possibilities. It was everywhere at once. But the moment, the exact nanosecond. The scientists looked at it. The electron stopped behaving like a wave and started behaving like a particle. It's as if the electron knew it was being watched. It's as if the universe said, "Oh, you're checking? Fine, here is a definite position. I will stop playing around." This phenomenon is known as the collapse of the wave function. Before measurement, reality is a superposition, a haze of probabilities. After measurement, reality collapses into a single, defined state. This destroyed the classical idea of an objective universe. In the old world, the moon is there whether you look at it or not. In the quantum world, the moon is only a probability distribution until you open your eyes. Albert Einstein hated this. He absolutely despised it. He famously said, "God does not play dice with the universe." He believed there must be hidden variables, secret gears and levers inside the electron that determine where it goes, regardless of whether we look or not. He refused to believe that reality was dependent on the observer. On the other side was Niels Bohr, the father of the Copenhagen interpretation. He told Einstein, "Stop telling God what to do." Bohr embraced the madness. He argued that there is no objective reality underneath. The properties of the electron do not exist until they are measured. It was the biggest debate in the history of science. The realist Einstein versus the instrumentalist Bohr. But as technology improved, experiment after experiment proved Bohr right. The universe really does seem to lack definite properties until an interaction occurs. But wait, it gets stranger. Scientists thought, maybe the detector is physically disturbing the electron. Maybe the light from the camera bumped into the electron and messed up the wave. That would explain it without magic. So, they tried to be gentle. They used weaker detectors. They used indirect measurements. It didn't matter. If you gained the information, if you knew which path it took, the wave collapsed. If you erased the information, if you destroyed the data from the detector, the wave came back. It wasn't about physical force. It was about information. The universe fundamentally cares about whether information is known or unknown. This leads us to the precipice of the simulation theory. In a video game, the computer engine optimizes resources. It doesn't calculate the physics of a falling tree in a forest if no player is there to hear it. It saves the RAM. It only collapses the code into audio and visuals when a player enters the zone. Is the collapse of the wave function just the universe optimizing its rendering pipeline? If you think that's the scariest part, you are wrong. Because decades later, physicists decided to push the boundaries of time itself. Chapter 4. The Quantum Eraser, 1999. The year is 1999. The movie The Matrix has just been released, making everyone question the nature of reality. And ironically, in that same year, a team of physicists performed an experiment that made The Matrix look like a documentary. It is called the Delayed Choice Quantum Eraser. If the Double Slit Experiment is the glitch, the quantum eraser is the blue screen of death. Here is the problem with the original experiment. You measure the electron as it passes through the slit. Skeptics could always argue that the measurement disturbed the particle at that moment. So, the scientists asked a crazy question. What if we measure it after it hits the wall? What if we let the electron hit the screen first, creating its pattern, and then we decide whether to look at which path it took? It sounds impossible. How can you measure the path after the journey is over? To do this, they used a special crystal, a BBO crystal. When a photon, a particle of light, hits this crystal, it splits into two entangled photons, twin particles. One is called the signal photon, and the other is the idler photon. Because they are entangled, they are effectively the same object. If you know the state of one, you instantly know the state of the other. Here is the setup, and I need you to visualize this carefully. The signal photon is sent straight to the double slits and hits the detector screen. This happens first. The journey is short. Bang! It hits the wall. Its story is over. The idler photon, the twin, is sent on a longer path, a much longer path. It travels through a maze of prisms, mirrors, and detectors. This path is designed to take more time. This means the signal photon has already hit the screen and made its mark before the idler photon reaches its detectors. The scientists set up the maze so they could make a choice. Choice A, they can capture the idler photon and see exactly which slit its twin came from, knowing the path. Choice B, they can scramble the idler photon so that the information is lost forever, erasing the path. Crucially, this choice is made after the signal photon has already landed. Common sense and the laws of time dictate that nothing we do to the idler photon now should change what the signal photon did in the past. The ink is dry. The history book is written. But quantum mechanics doesn't care about your history book. When the scientists looked at the data, their minds were blown. If they chose choice A, checking the path of the idler photon in the future, the signal photon in the past formed a particle pattern, two bands. If they chose choice B, erasing the information in the future, the signal photon in the past formed an interference pattern wave. Read that again. The photon hitting the screen in the past knew what the scientists were going to do in the future. It effectively said,
"Oh, you're going to destroy the information 5 nanoseconds from now. Okay, I'll behave like a wave right now." Or, "Oh, you're going to check the detectors?
Okay, I'll behave like a particle right now." This is retrocausality, the future influencing the past. It implies that time is not a one-way street. In the quantum realm, before and after are blurry concepts. The state of the system is determined by the entire timeline, not just the preceding events. Or, if we look at it through the lens of simulation theory, the data isn't processed until the loop is closed. In computer programming, this is called lazy evaluation. A program delays the evaluation of an expression until its value is actually needed. The computer doesn't decide what the signal photon did until the logic of the idler photon is resolved. The past is just a variable in the memory buffer, waiting to be finalized. It suggests that history is not fixed. History is a set of probabilities that only harden into fact when we have the information to confirm them. And if the future can change the past on a quantum level, do we really have free will? Or is the script already written, and we are just playing it out? Chapter 5. Many worlds: the alternative explanation. Now, before we fully commit to the idea that we are living in a computer, we must look at the only other theory that makes mathematical sense. It is the only theory that saves realism, but the price it pays is arguably even higher. It is called the many worlds interpretation. Proposed by Hugh Everett in 1957, this theory looks at the double slit experiment and says the wave function doesn't collapse. The electron doesn't choose to be in the left slit or the right slit. It is in both. But wait, you say. We saw it go through the left slit. The detector beeped. Everett would say yes. You saw it go through the left slit, but there is another version of you in a parallel universe who saw it go through the right slit. According to many worlds, every time a quantum event has multiple possible outcomes, all of them happen. The universe splits. Ideally, it branches. In one branch of reality, the electron went left. The scientists in that branch wrote down left. In another branch, the electron went right. The scientists in that branch wrote down right. In another branch, the electron went through both. These branches are constantly splitting, creating an infinite number of parallel universes every single nanosecond. There is a universe where you stopped watching this video 5 minutes ago. There is a universe where you never clicked on it. There is a universe where humans never existed. This explains the interference pattern without magic. The electron interferes with its own counterparts from other universes. The ghost waves are actually bleeding over from parallel realities. When we measure the particle, we aren't collapsing the wave. We are simply finding out which branch of the multiverse we are currently standing in. It solves the paradox. It removes the spooky action of the observer. The observer isn't creating reality. The observer is just riding one specific track on an infinite railway system. But ask yourself, which is scarier? Scenario A, we live in a simulation where reality is only rendered when we look. The universe is fake. Scenario B, we live in a multiverse where every tragedy, every nightmare, and every horror that can happen does happen in some parallel world. The universe is infinite and indifferent. Most modern physicists lean towards the Copenhagen interpretation probabilities, or many worlds. But a growing number, backed by tech moguls like Elon Musk and philosophers like Nick Bostrom, are looking back at the information aspect. They are looking at the pixels. They are looking at the speed of light. And they are starting to see the bars of the cage. If the universe is made of math, and math is the language of code, then who wrote the code? Chapter 6. The limits of the processor speed of light. If the many worlds theory feels too chaotic, too infinite, then we are left with the final, and perhaps most scientifically robust explanation. The one that explains why the universe optimizes data. The one that explains why the wave function collapses. The simulation hypothesis. If you look closely at the fundamental laws of physics, you start to see things that look suspiciously like computer code. Specifically, you see limits. In any video game or software simulation, there are hard constraints determined by the hardware running it. There is a limit to how fast the processor can calculate changes. There is a limit to the resolution of the graphics. Does our universe have these limits? Yes. First, look at the speed of light: 299,792,458 meters per second. It is the cosmic speed limit. Nothing in the universe, no matter, no information, no signal can travel faster than this speed. But why? Why that specific number? And why is there a limit at all? In a perfectly analog physical universe, you should theoretically be able to push something faster and faster forever, as long as you have enough energy. But you can't. You hit a wall. In a computer simulation, this makes perfect sense. The speed of light isn't a speed, it's a latency limit. It represents the maximum speed at which information can be transmitted across the grid of the simulation. It is the clock speed of the universal processor. If you try to move an object faster than the refresh rate of the server, the causal chain breaks. The game crashes. So, the code has a hard-coded cap. And what happens when you try to break the code? What happens when you pile too much mass into one spot, demanding more processing power than the system can handle? You get a black hole. A black hole is a region where gravity is so strong that not even light can escape. But look at it through the lens of a programmer. A black hole is a divide by zero error. It is a point where the math of the universe breaks down. It results in infinity, which computers cannot handle. So, what does the system do? It quarantines the error. It wraps it in an event horizon, a firewall that prevents anyone outside from seeing the glitch inside. It prevents the crash from spreading to the rest of the server. The double slit experiment is just another example of this efficiency. Why render the precise path of an electron when no one is looking? It's a waste of RAM. Just keep it as a probability distribution, a wave, until a player and observer queries the database. It's efficient. It's logical. It's exactly how we would build a universe. Chapter 7. The Pixelated Universe Planck Length. But the smoking gun isn't just the speed, it's the resolution. If reality is real, if it is a continuous, smooth fabric, then you should be able to zoom in forever. You should be able to divide space into halves, infinitely. Half a meter, half a millimeter, half a nanometer, down to infinity. But quantum mechanics says no. You cannot zoom in forever. There is a hard limit to how small you can go. It is called the Planck length. It is approximately 1.6 times 10 to the power of negative 35 meters. If you try to measure anything smaller than this, the concept of distance ceases to exist. Physics dissolves. This means our universe is not smooth. It is discrete. It is made of tiny, indivisible chunks. Do you know what else is made of tiny, indivisible chunks? A computer screen. Pixels. The Planck length is the pixel size of our reality. It is the grid upon which the simulation is rendered. If space is pixelated, and energy comes in packets, quanta, then the universe is digital. It is not analog. And if it is digital, it is computed. Physicist John Wheeler, one of the giants of 20th century science, summed this up with the phrase "it from bit." He meant that every particle, every force, every atom is ultimately derived from a bit, a binary unit of information. Yes or no, 0 or 1. The electron goes through the left slit 0, or the right slit 1. The wave function collapses 1, or it doesn't 0. The double slit experiment was the first time we saw the code behind the interface. We saw the system hesitating. We caught the rendering engine in a moment of uncertainty. We are not living in a solid universe. We are living in a sea of information. Chapter 8, The Architects. This leads to the final, haunting question. If this is a simulation, who built it? And why? Oxford philosopher Nick Bostrom proposed the simulation argument. He stated that at least one of the following three propositions must be true. 1. Civilizations almost always go extinct before they reach the tech level to run realistic simulations. We are doomed. 2. Advanced civilizations can run simulations, but they choose not to. Unlikely, given human curiosity. 3. We are almost certainly living in a simulation right now. Think about it. In just 50 years, we went from Pong 2 rectangles and a dot to photorealistic virtual reality. If we continue to advance for another 1,000 years, or 10,000 years, we will inevitably build computers powerful enough to simulate a universe. We will build ancestral simulations, virtual worlds to study our own history. We will populate them with billions of AI minds. Minds that think they are real. Minds that feel love, fear, and curiosity. Minds that perform the double slit experiment and wonder why the electrons are behaving so strangely. Statistically, there will be millions of these simulations, but only one base reality. The odds that we are in the one, original, biological reality are 1 in billions. So, who are the architects? Are they our descendants, studying us to learn from our mistakes? Are they an alien intelligence, running a test to see how life evolves? Or are we just a screensaver, a forgotten program running on a server in a basement gathering dust? The double slit experiment suggests that the simulation is interactive. It responds to us. It responds to observation. This implies that consciousness is not just a byproduct of the code, it might be the purpose of the code. Perhaps the system is designed to be observed. Perhaps the wave function collapses because the simulation requires a player to define the narrative. Conclusion: waking up. The double slit experiment started as a debate about light. It ended as a revelation about the nature of existence. We learned that matter is not solid. We learned that the past can be rewritten by the future. We learned that reality requires an observer to snap into focus. It is unsettling. It makes the ground beneath your feet feel a little less stable. But there is beauty in it too. If the universe is a machine, it means it can be understood. If reality is code, it means it can be debugged. And if we are the observers who collapse the wave function, then we are not insignificant specks of dust. We are the engine that drives creation. We are the eyes of the universe, observing itself. Science has brought us to the edge of the map. We have peered through the double slits and seen the gears turning behind the curtain. We can choose to ignore it. We can go back to believing that the world is solid, predictable, and boring. We can take the blue pill, or we can accept the glitch. We can accept that reality is fluid, malleable, and deeply connected to our own minds. The next time you look in the mirror, ask yourself, are you looking at a physical face? Or are you simply a cluster of data, observing a reflection, and in that act of observation, willing yourself into existence? The experiment is not over. We are the experiment, and the simulation is just getting started.